Hello, everybody. Welcome to the second video for week 2. So today the video is about continued fractions, the Euclidean algorithm, and uniqueness of prime factorization. So what we're going to do today is first we're going to formalize some ideas about continued fractions that we introduced in class and the connection with the Euclidean algorithm. Then we're going to explore sort of another consequence of the Euclidean algorithm. It's a theoretical consequence called the fundamental theorem of arithmetic. And using that, we're going to establish the uniqueness of prime factorizations. So if you recall from earlier, we've already seen that every number can be every positive integer can be factored into primes. So it can be written as a product of prime numbers. But we haven't yet shown that that expression is unique. So that's where we're going to get to today. Okay, well, starting with continued fractions. So we saw continued fractions in class on Tuesday. So I just wanted to introduce some notation to make it a little bit easier to talk about them. So if I have an A0 and Z, and then a list of n positive integers, so just A0 can be any integer, but A1 through AN are going to be positive integers. Then I denote by this notation with brackets, and then A0 is sort of set off with a colon, then A1 through AN are just set off with commas. So this is just a symbol that's shorthand for the continued fraction, where I do A0 plus 1 over A1 plus 1 over A2 plus 1 over and so on plus 1 over AN. So this is the kind of thing we saw in class on Tuesday. And this is just some compact notation for writing that. So A0 is sort of set off because A0 is the only thing that doesn't appear under a denominator, so it's allowed to be an arbitrary integer. So in particular, the most important thing with these AIs being positive integers is probably just that they're not 0, because otherwise, like for example, if AN was 0, then you'd have a division by 0. Okay, and so if you let them be negative, then you could sort of end up with a division by 0 just by cancellation. So that's why we require these to be positive integers in this notation. Okay, so that's sort of the first notation. And then we saw right at the end of Tuesday's lecture, when we looked at square root of 2 and applied this process for expressing it as a continued fraction, that's also interesting to allow an infinite sequence of positive numbers. So instead of chopping off at some n, these are just keep on going. And so here we define an infinite continued fraction. So same notation, but A0 colon A1, A2, A3, and now this list never ends. So this is a sequence instead of just an infinite sequence instead of just a list of n numbers. Well, we just define that to be the limit as n goes to infinity of these finite continued fractions. So just like when you're defining an infinite sum, you really define it to be the limit of the partial sums as n goes to infinity. So this sort of nth step is called the nth partial convergent. And it's a theorem that we won't discuss, but we can prove that this converges to a real number. I guess this is actually probably the n minus 1th partial convergent. So it's not the first partial convergent, it's just if you do A0, then A0 and A1, that's the second partial convergent, and so on. Okay, and sometimes we write that as sort of, we write that using this notation where we have this continued fraction, and then we just have a dot, dot, dot down here instead of terminating at some AN. But this notation, like this dot, 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 means take this limit. Yeah, so if you've taken some calculus analysis, it's a good exercise to prove that this sequence converges. We're just going to take that on faith. Okay, so good, but this is just notation for this idea that we introduced in class on Tuesday. But let me recall the examples we discussed. So we talked about how 60 over 22 has this notation 2, 1, 2, 1, 2. Okay, and then at the end of class, we saw that square root of 2 is 1, 2, 2, 2, 2, 2, and so on. Okay. If you're expressing just an integer in this notation, then you don't have anything after the colon. So just 17 is 17 colon. So this sort of first entry describes the integer part, and then sort of the things that come after describe the fractional part. Okay, good. Then if you work it out for pi, you can just do it with a calculator or by hand, and you'll get these for the first few digits of the first few entries of the Canadian fraction expansion. And I just wanted to highlight that if I look at the fourth partial convergent, so 3, 7, 15, 1, and I expand that out. So and if I ever take one of these finite partial convergents, I can just unravel it until I get a fraction. So if I did that for this one, I unraveled it, I'd get 355 over 113. And if you compute that decimal expansion, you have 3.14159929. And that's a pretty good approximation of pi, actually. So pi is 3.1415926 and so on. So these agree on the first 6 digits after the decimal place, which is pretty impressive because like this is just a quotient of 2 3-digit numbers. Whereas if you think about like, what this decimal expansion means, like if you went out to this point, that'd be the quotient of a 7-digit number by a 10-digit number. So that's like this by this over, or yeah, so a 7-digit number by a 7-digit number. Okay, so somehow this is a lot better. And that's what I think about continued fractions. They tend to give very good approximations for numbers. And so you'll see one of the worksheet exercises that like you'll do this for square roots. You'll sort of see how close the partial convergents get. Okay, so state a theorem about continued fractions. Let's call this the continued fraction algorithm. So there are really 2 parts. The first says that if I have a real number, alpha, then it has a continued fraction expansion. Moreover, this is a unique expansion. And so, well, that expansion is going to be infinite or it's going to be finite. And it's going to be finite if and only if alpha is a rational number. And to compute it, well, you just follow the algorithm that we did in class, but let me sort of spell it out a little bit more. First, you take alpha naught to be equal to alpha. You set sort of AI to be the floor of alpha. And so this is the AI are going to be the coefficients, the entries in your continued fraction expansion. Beta I is going to be alpha I minus the floor of alpha I, so the fractional part. And if beta I is equal to 0, you stop. And otherwise, you set alpha I plus 1 to be the reciprocal of beta I. And then you go back to step 1, but now for I plus 1. So you get sort of alpha is equal to A0, A1, A2, AM, or so this is if you stop. Or if you don't stop, then you just get A0, A1, A2. So you're going to stop exactly if alpha was a rational number. Okay, so I'll run this algorithm in a second, just with this 60 over 22 that we already did in class. But I want to point out that if you look at square root of 2, so by the way, if you didn't finish this in class, you should take a moment now and go look and sort of try and justify for yourself, this is the continued fraction for square root of 2. But okay, and if you believe this theorem, then this gives you another proof that square root of 2 is not rational, because this is an infinite continued fraction expansion, so this never stopped. So that means square root of 2 is not a rational number, because this theorem says that if it was a rational number, then the continued fraction expansion would be finite, so it's stop at some point. Okay, good. And so if you remember on the first worksheet, we gave a proof of this using prime factorizations. Now this is another way you can prove it. Of course, there are many other ways to prove it still. Okay, so let's run this algorithm for 60 over 22, our favorite example. That's alpha. So the first step of the algorithm says that alpha naught equals alpha, so that's what I bring here. Alpha naught is 60 over 22. Okay, and then next thing is set A0. So we sort of start at 0, I equals 0, and we set A0 to be the floor of alpha 0. There should be an alpha I up here. So the floor of 60 over 22, well, that's just 2. And then the fractional part is 16 over 22. And then the reciprocal is 22 over 16. And that reciprocal, so beta I was the fractional part, so that's what I put here, so beta 0. And then the reciprocal, so the next, so alpha 1 is 22 over 16. So alpha I plus 1 is just the reciprocal of beta I. Okay, good. So now I keep on going. So now I take the fractional part of 22 over 16, I just get 1. And then I do I take the integer part, so the floor of 22 over 16, and I get 1. Then I take the fractional part, is going to give me 6 over 16. And I take the reciprocal, 16 over 6. And okay, now I take the floor versus the integer part is 2 of 6 over 16 over 6. Then I take the fractional part. This is 4, 16 again, sorry, 4 over 6. This is this computation we keep on doing. And then the reciprocal is 6 over 4. Okay, so then the integer part is 1, fractional part is 2 over 4, reciprocal is 4 over 2, and that's 2. So then the integer part has 2, but that's actually the whole thing. So the fractional part is 0, and that means we stop. Because you remember, in this algorithm, if ever you get to a point in this table where beta I was equal to 0, so if ever you hit a 0 in this entry of the table, then you stop, and you've got your fraction expansion. So we recovered, so 60 over 22 is equal to 2 colon 1, 2, 1, 2. So you read the continued fraction expansion down this column. Okay. And let's just recall that the GCD of 60 and 22 was equal to 2. And we computed that using the Euclidean algorithm. So here I've written out the steps. Good. And then so the last non-zero remainder was 2, that's why it's the GCD. But then if you look at the multiples, so the sort of Q's that appear in the Euclidean algorithm, it's 2, 1, 2, 1, 2. And well, this is the continued fraction expansion of 60 over 22. So it's 2, 1, 2, 1, 2, really is the same one here. And if you sort of follow through what you're doing here, and you're really doing the same computation in the continued fraction expansion as you were doing in the Euclidean algorithm. And that's something we'd already observed in class on Tuesday. This really sort of holds generally. So if you have alpha a rational number, so alpha is A over B, then you sort of do the Euclidean algorithm to compute the GCD of A and B, like this. So the GCD will be sort of this last non-zero remainder, Rm. Right, so you get this thing, and well, that's this last non-zero remainder is the GCD. But then if you look at these Q's that are appearing, those give you the continued fraction expansion. So just like in this case of 60 over 22, this happens generally, and it's all because really they're the same computation, just sort of written different ways. Okay, so and that's actually how you prove the first part of this theorem. So which part? This is how you prove that the continued fraction expansion is finite if and only if alpha is containing Q. So that shows that we already know the Euclidean algorithm terminates at some finite step. And so once you have the relation, that shows that if you have a rational number, then definitely has a finite continued fraction expansion. And then the other direction, if you have a finite continued fraction expansion, well, then you sort of just expand out and collapse until you get a rational number. So that justifies this point. And we're not going to justify this point. I'm just going to tell you this is a fact, that any alpha in R has unique continued fraction expansion, and sort of it's given by this algorithm. So, and what's left to do is to prove that the continued fraction you get really converges, and it converges to alpha. So that's a good exercise, again, if you've had some basic analysis, but we're not going to discuss it further in this class. Okay, so good. So I wanted to sort of say those things about continued fractions, and we'll touch back on this relation between continued fractions and the Euclidean algorithm one more time today. But now I want to get back to unique factorization. So the main thing we need out of the Euclidean algorithm and sort of this whole picture that we've been doing in GCDs is we're going to get a tool that's going to let us prove the uniqueness of prime factorizations, and that tool is this theorem. So this is called the fundamental theorem of arithmetic in the book, but some people call sort of unique factorization the fundamental theorem of arithmetic. So try not to use that terminology too much. And this says that if a and b are two positive integers, then there are two other integers, x and y, such that ax plus by is equal to the GCD of a and b. So this is saying that if you have two positive integers, then you can write their greatest common denominator as a linear combination of those two numbers, where the coefficients of your linear combination are integers. Okay, so I'm going to just give an example that sort of explains the proof idea. And the example, and the idea is just you do the Euclidean algorithm and then you unfold back up. So let's do that for 60 and 22. So A is 60, 22 is B. We know the GCD is 2, and we know that from doing the Euclidean algorithm. So this is what we got. Okay, now we're just going to sort of unfold back up to get an x and y that combine that sort of such that ax plus by is the GCD of 60 and 22. So we're going to start by we want to start by finding where the GCD appears. So the GCD appears in the second to last equation. So it's the last non-zero remainder, so it's appearing right here. And we can take this equation, we can rewrite it as giving a formula for 2. Let me actually get that here. So I get 2 is equal to, we write 1 times 6 minus 1 times 4. Okay, so I just moved this 1 times 4 over to the right, and I sort of rewrote 6 as 1 times 6. So this dot is times. Okay, and now I'm going to use the other equations to sort of make these numbers 4 and 6 bigger until I only have sort of 22 and 60 appearing, some multiples of them. So I'll start with the smallest one. So first I should do this to 4. So I get this is equal to 1 times 6 minus 1 times, okay, so how do I write 4? Well, here I use this equation to rewrite 4. So 4 is 16 minus 2 times 6. Okay, and then if I gather terms, now I have minus 1 times 6. Or sorry, not right. I have 3 times 6. So 1 times 6, then minus 2 times 6. Plus 1, sorry. Let me write this, say plus minus 1 times 16. Okay, so now I've sort of improved my situation because I've sort of moved up. Instead of having 4s and 6s, I have just 6s and 16s. So I sort of moved up this tower, and I keep on going. So now I'm going to do this for 6. So 6 is, I use this equation to solve for 6. So 6 is 22 minus 1 times 16. So this is 3 times 22. Then I have minus 3, so minus 4 times 16. Yeah, good. You could check this every step. I mean, this should still be equal to 2, and this is 66 minus 64. That's good. This is still equal to 2. Good. So we keep on going, and we have a 22 now. And 22, is one of the numbers we started with. So that's sort of, it's good to have some multiple of 22, but we need to get rid of the 16 still. And so we use this last equation at the top. 60 is equal to 2 times 22 plus 16, and we solve for 16. We get, so this is 3 times 22 minus 4 times 1 times 60 minus 16. Sorry, minus, not minus 16, minus 2 times 22. Okay, and if we do this out, then we got, we group them, I got minus 4 times 60. And then, so we get to plus 8, so plus 11 times 22. That's minus 240 plus 242. So good, that still is 2. And so this is this is my x, this is my y. If I just order this, so ax, so 60 times minus 4 plus 11 plus 22 times 11. So x, y equals 2. And that's what we want to get. We want to get some number times x, or so a times some number x plus b times some number y was equal to GCD. So here a is 60, b is 22, so we want 60 times some number plus 22 times some number is equal to GCD2. Okay, so good. So that's how we do it, how you sort of unfold and find the solution in this specific case. But it should be pretty clear now that this, like if you just do the Euclidean algorithm for computing the GCD and unfold in this way, no matter what a and b are, you're always going to be able to do this to find a solution. So that's sort of why this fundamental theorem of arithmetic, why the statement is true. Okay. Want to make just a remark connecting this back to the continued fraction expansions, because it's sort of convenient sometimes. So if I do 60 over 22, we just have the continued fraction expansion 2, 1, 2, 1, 2. Again, I can write out the partial convergence. So the first and fifth partial convergence. The first one's 2. The first one is what's 2 plus 1 over 1. Say 3. Then 2 plus 1 over 1 plus 1/2. Well, if I expand that out, I'm getting 8/3. Then similarly, if I expand this next one out, I'm getting 11/4. And then the final one, which is equal, the whole thing is 60 over 22. So you have 5 terms. The fifth partial conversion is equal to the thing. But let's step back one and look at the fourth partial convergent. And we see this 11 and 4 that showed up already in the fundamental theorem of arithmetic. So this is no accident. Actually, you can always sort of build a solution to ax plus by. So you can always sort of get x and y by taking this second to last partial convergent and looking at its numerator and like the negative of the denominator. So we're not, I won't explain this any further, but it's sort of a fun thing for you to think through why this works. But this is a convenient trick to know sometimes, because if you've already computed the partial convergence, then you can sort of use that to find the solution without having to sort of go back and unfold the Euclidean algorithm again. Okay, great. So we've established more or less the fundamental theorem of arithmetic. And now I want to explain how to use this to justify unique factorization. So it gets used to prove a lemma. I'm going to make some room for this actually. Sorry about that. Okay, so now I have room to prove this lemma. So the lemma says that if I have a prime number, p, and I have 2 integers a and b, such that p divides a times b. So that's the hypothesis. I have prime number, 2 integers, and p divides their product. Then the key thing is that then actually p has to divide either a or p divides b. So if it divides the product, then it must divide one of the 2 numbers. Okay, and then more generally, if p divides a1 times a2 times an, so these ai's are all integers, if p divides a product of integers, then it must divide one of those integers. So this is true for prime numbers. It's not true for arbitrary integers. Of course, like 12 divides 3 times 4. 12 is equal to 3 times 4, but 12 does not divide 3 and 12 does not divide 4. But if you're a prime number, then this is true. So if you divide the product, you have to divide one of the terms. Okay. Somehow this more general case where I multiply like n things, you can reduce it to the first case by grouping terms. So the key thing is sort of just this statement when I have two things, and it's just A and B. So let me justify that. Okay, and so I'm going to sort of assume P divides AB, and so because I have P divides AB, that is equivalent to saying AB is sort of Q times P for some integer Q. So I'm going to use that in a minute. Okay, and so then, well, I'm trying to deduce that P divides A or P divides B. So let me just suppose P does not divide A. Then I need to show that if P doesn't divide A, it divides B. Okay, but since P does not divide A, this means that the GCD of P and A is 1. This is just because, I mean, the only divisors of P are 1 and P. So, well, the GCD of P and A is, in particular, it's a divisor of P and it's a divisor of A. So if this is a divisor of P, it has to be either 1 or P. And, well, it's also a divisor of A, and I just said P doesn't divide A. So it can't be P, so it has to be 1. Okay. Good. So I get that the GCD of P and A is equal to 1. And then, so this fundamental theorem of arithmetic tells me that there are integers. So this little sign means there exists X and Y and Z, such that P times X plus A times Y is equal to 1. Okay. So let me sort of multiply that by B. So I'm just going to multiply this equation by B. I get P times X times B plus AB times Y is equal to 1. Then I sort of substitute, so I get P times X times B plus then, so AB is sort of Q times P, which becomes Q times Y. Sorry, over here I have a B because I multiplied both sides of this equation by B. Okay, now it's just rewriting this by factoring out the P from A times B. So as up here, this is equal to B. Okay, so this literally says that P divides B because B is P times this thing. So I assume P doesn't divide A. I was able to deduce that P divides B. And so the key thing that let me do this was the fundamental theorem of arithmetic. So finding this X and Y. Okay, excellent. Good, so using that, we can now, so using this lemma, we can prove the uniqueness of factorization. So let's do that. So let me suppose I have a positive integer n, and let me suppose I have two potentially different ways to factor as a product of primes. So P1 times P2 up through PR, and Q1 times Q2 up through QS, where sort of to make, remember there's this ordering statement in the uniqueness theorem, and so I'm ordering these, so P1 is less than equal to P2, is less than equal to P3, is less than equal to PR, and so on. The QIs are non-decreasing as well. Okay, so this isn't quite how I wrote the statement before. Like I had sort of PI to the AI and P2 to the A2 and so on when I was writing prime factorization earlier. And then I had sort of strict less than here. And I'm sort of just expanding out each of these PI to the AIs. So for example, if 12 is 2 squared times 3, I just rewrite that as 12 is 2 times 2 times 3 to get this kind of expression. And so a priori, like R might not be equal to S even, like it might not even be the same number of factors over here. Okay, but I want to sort of show there are, as I really want to show sort of, so I want to show I want to show R is equal to S, and Pi equals Qi for all I. I want to show these really actually have to be the same. And I'm going to use that lemma to do it. I'm going to make one quick hypothesis. Up to like swapping what I'm calling P's and what I'm calling Q's, I can assume that P1 is less than or equal to Q1. Okay, and then when I do that, well, P1 divides N because of this expression, which is equal to Q1, Q2, product all the way up to QS. Okay, so the lemma implies P1 divides Qi for some I. Well, but these are Qi's are non-decreasing. I assumed P1 is less than or equal to Q1. So the only way you can sort of divide one of them just by size considerations is sort of if it divides the first one. But and P1 is not equal to 1. So it must be the only other divisor of Q1, because Q1's prime. So only divisors are 1 in itself, so P1 has to be equal to Q1. Okay. So then cancel P1 equals Q1 and get now P2, P3, and so on. PR is equal to Q2, Q3, QS. And now sort of you have one fewer factor on each side, and you repeat. Okay, and so when you repeat, you're going to get sort of P2 is equal to Q2, and then you factor out, and then sort of you're just going to keep on going, and you'll get all the way through, and you're going to have to stop at the same time because sort of R is not equal to S. So like say S was bigger, you get sort of 1 over here is some product of primes, and so that can't happen. Okay, and that's the idea, and then you're done. Now we understand why uniqueness of prime factorization holds. So I'll see you in class on Thursday.